Hello, welcome to another module in this massive open online course on applied linear algebra for signal processing, data analytics and machine learning. So, let us start our lecture. Alright, so we are going to start with the fundamental concepts of vectors and how vectors can be used to represent data. Alright, so this is the massive open online course on applied linear algebra for you have SP and you have also the DA, that is your data analytics, and also you have ML, which is basically so as you can see, essentially linear algebra and its applications, the concepts of linear algebra are so fundamental that they have diverse applications. In fact, they are applied in almost all the fields of science and engineering, and in particular we are going to look at the interesting applications of linear algebra in signal processing, data analysis, data analytics and machine learning. Alright. So, the notion of linear algebra, when we talk about linear algebra, the notion or concept of vectors, correct. So, vector or basically n dimensional point is fundamental, right. This is fundamental to represent data as well as this is fundamental to represent data. For instance, we can define a vector u bar as this is an n dimensional vector u bar equals comprising of the elements, or we say the components u1 u2 un. This is we say n dimensional vector, correct. So, this is an n dimensional vector, and this is fundamental to represent the data, which is what we are seeing, and this belongs to the n dimensional real space. So, this notion is basically your n dimensional real space if u1 u2 so on up to un, if these are real, right, else this belongs to the n dimensional complex space, right. So, this is n dimensional complex space if your u1 u2 un are complex. So, you have the n dimensional vector u bar, if u1 u2 un are real, then this belongs to the n dimensional real space. If u1 u2 un are complex, this belongs to the n dimensional complex space, alright. Okay. And this remind you can also say u bar represents this essentially represents an n tuple, or essentially you can also say this is a point in n dimensional space. This represents an n tuple or a point in n dimensional space, and by default we will consider real vectors. Okay, so by default we will consider real vectors. For example, a classic example of that for our course would be an n dimensional signal, right, n samples of a signal. So, you take continuous time analog signal, you sample it and you consider n samples of the signal, that would be a vector, right. So, you take for instance a classic example, a very useful example for us. So, this is your signal, and then you take the n samples. So, these are the samples. So, n samples of a signal in space, sorry, n samples of a signal in time, or we can generally say n samples of a signal, all right. So, that will be your signal vector, all right. So, for instance, you have n samples of noise, that can be your noise vector. So, vectors have a lot of applications. Of course, you can consider n samples of a spatial signal such as an image, right. So, of course, image is 2 dimensional, but you can also take the samples and put them as a vector, all right. So, essentially vectors are very useful in representing data, signals and various other quantities, right. Therefore, now for instance, you can also have the n observations of a sensor, right. So, that can also be another interesting vector. So, n observations of a sensor in time, such as temperature, pressure, right. For instance, let us write this another example. You can have n observations of a sensor such as temperature, pressure, etc. Okay, so that is your there are basically many examples of such vectors. Okay. All right. Now, for instance, a location in a 3D space, that can be represented by, or you have a location in 3D space that can be represented by a 3-dimensional vector. Any location in 3D space that can be represented by the 3-dimensional vector u1, u2 through 3, or what we call as the x, y, z coordinates, all right. So, this is basically a 3-dimensional vector. This is the physical space that we are used to. This is your location in 3-dimensional space. Now, consider 2 n-dimensional vectors. Now, let us look at vector addition, right, vector addition. Consider 2 n-dimensional vectors. that is we have, let us say, u bar equals u1 u2 un, and we have v bar equals v1 v2 vn, then the vector addition is simply an element by element addition of these two vectors. So, essentially u bar plus v bar will also be an n dimensional vector with the first element u1 plus v1, second element u2 plus v2, so on, nth element un plus vn. Okay. So, u bar plus v bar will also be an n dimensional vector with first element u1 plus v1, u2 plus v2 and nth element un plus vn. And let us now consider the scalar product. Let us consider the scalar product. You have u bar plus v bar, or you have k, that is a scalar. So, k is a scalar coefficient. So, k times u bar, you take the scalar, multiply it by each element of the vector. So, this will be k u1, k u2, so on up to k u n. Okay. And then we have the notion of a linear. So, this basically completes the basic operations, that is your what we call as your vector addition and the scalar product. And now let us look at another fundamental operation of vectors, that is basically a linear combination. Okay. So, let us now look at a linear combination let us now look at a linear combination of vectors. So, you have the vectors u bar, u1 bar, u2 bar, um bar. So, consider the vectors um bar, these are the vectors, and then you have the scalar quantities k1, k2, km, these are your scalars. Then your linear combination of vectors, the linear combination is basically given as multiply each scalar coefficient by the corresponding vector. So, this is essentially your linear this is essentially the concept of the linear combination of the vectors, right. So, this is the linear combination of vectors. Then we have the notion of an inner product, right. So, that is basically, and this is a very important concept, the linear combination of the vectors. All right. Now, let us consider another concept, that is the inner product. What about the inner product? And this is another fundamental concept, that is the inner product. When you have two n dimensional vectors, what happens to the inner product of these two vectors? right. So, consider arbitrary vectors u bar comma v bar that belong to the n dimensional space of real vectors, that is you have u bar equals u1 u2 up to un and v bar equals v1 v2 up to vn. Then we have u bar transpose this becomes a row vector, right. U bar transpose, when you take the transpose of a column vector, that becomes a row vector. So, this is u bar transpose, and then so this is u bar transpose is essentially a row vector, okay. And then we define the inner product. This is a very important definition. We define the inner product of u bar v bar, we define it as u bar transpose v bar, which is essentially, if you look at this, this is the product of the row vector u1 u2 un times the column vectors v1 v2 vn, which is equal to summation I equal to 1 to n. I can write it as ui vi, or essentially this is u1 v1, write it in the expanded form u1 v1 plus u2 v2 plus un vn, okay. So, this is basically the notion of the inner product. So, this is the inner product. And this is a very important concept, the concept of an inner product between two vectors. For example, let us take these two vectors, example u bar equal to 2 1 minus 1 and v bar equal to 1 minus 1 3, and then what you can say is you have u bar v bar, the inner product is u bar transpose v bar, which is basically equal to 2 1 minus 1 and 1 minus 1 3, which is essentially equal to 2 minus 1 minus 3, which is equal to minus 2, alright. So, that is a simple example for the inner product, which is essentially you can also think of it as an element wise multiplication of two vectors and then an addition, that is u1 v1 plus u2 v2 so on until un vn, okay. Now, for complex vectors the definition becomes we have u bar, the inner product of u bar v bar, we will define this as u bar Hermitian v bar, that is essentially you have to take the transpose, that is when you look at the Hermitian you essentially have to take the transpose and also the complex conjugate u1 conjugate u2 conjugate un conjugate times v1 v2 vn, that is sigma I equal to 1 to n, that is ui conjugate vi, alright. So, this is the notion of inner product for complex vectors u1 conjugate v1 plus u2 conjugate v2 plus u1 conjugate vn. Okay. Further, now there is a notion of orthogonality which is very important. Right, the notion of orthogonality of two vectors. Two vectors are and this is a very important property. Two vectors are orthogonal if their inner product is 0. Okay. So, orthogonality, two vectors are orthogonal or perpendicular. Orthogonal, I am sorry, orthogonal if their inner product equal to 0. So, the two vectors are orthogonal, that is in real dimensions we have u transpose v bar equal to 0, that is for the r dimensional space, for the n dimensional real space. For the complex space we have u bar Hermitian v bar equal to 0. So, this is essentially the definition of orthogonality. Let us take a look again at another simple example. U bar equals 1 minus 1 1 minus 1 and v bar equals 2 2 minus 2 minus 2, and we have u bar transpose v bar. If we do u bar transpose v bar, this will be 1 minus 2 minus 2, I am sorry 2 minus 2 minus 2 plus 2, which is equal to 0. So, these two vectors that you have over here so, these two vectors are orthogonal. Essentially what we also say informally as these two vectors are perpendicular, and that makes more sense in 3-dimensional space, that is we have two vectors which are at right angle with respect to each other, right. More generally the notion is these two vectors are orthogonal because their inner product is 0. Okay. Let us look at another interesting example, and this time with respect to complex signals and complex sinusoids, alright. So, another very important example, I would also say consider the complex sinusoids. For instance, you have the sinusoids u bar, let us call this as your 1 e raised to j 2 pi over n e raised to j 4 pi over and so on and so forth, e raised to j 2 pi n minus 1 over n, alright. So, this is your first sinusoid, and then you have another which is essentially e raised or 1 e raised to j 4 pi over n e raised to j 8 pi over n, so on and so forth, right. So, this is essentially, I am sorry, this has to be e raised to j 3 pi over n, this has to be e raised to j 6 pi over n, and so on and so forth, e raised to j 4 pi n minus 1 over n. So, you can see these are essentially two complex sinusoids. These are essentially two complex sinusoids. I am sorry, let me make this again. This has to be 4 pi over n, and this has to be 8 pi over n, and essentially what you have, essentially these are two complex sinusoids and if you look at their inner product, so these are two complex sinusoids corresponding to the frequencies. If you look at the frequency of this, that is f1, this will be equal to 1 over n, and this will be a complex sinusoid of frequency f2, this will be equal to 2 over n, right. So, you are talking about the complex sinusoid e raised to j 2 pi f n f1 n e raised to j 2 pi f2 n, all right. And when you look at their inner product, u Hermitian V is basically, if you look at this, that will be the summation L equal to the summation L equal to 0 to n minus 1 e raised to minus j 2 pi L over n e raised to j 4 pi L over n, right, and therefore, this is going to be the summation L equal to 0 to n minus 1 e raised to j 2 pi L over n, which is essentially 1 minus e raised to j 2 pi n over n divided by 1 minus e raised to j 2 pi over n. And if you look at this, e raised to j 2 pi n over n is nothing but e raised to j 2 pi, which is 1. So, this is 1 minus 1 divided by 1 minus e raised to j 2 pi over n, which is 0, all right. So, therefore, you have this interesting property where you have the complex sinusoids at the frequency 0, 1 over n, 2 over n, and so on n minus 1 over n. These are essentially orthogonal, all right. So, we have the interesting property complex sinusoids at frequencies. So, you have complex sinusoids at the frequencies at the frequencies 0, 1 over n, all right. Complex sinusoids at these frequencies, these are orthogonal. Complex sinusoids at this, and this property, right, this orthogonality of this complex sinusoids, this property is extremely important in Fourier analysis. This forms the basis of all Fourier analysis, right. So, this property in fact, this property is very important in Fourier analysis, and in fact, this forms the basis for all Fourier analysis. So, it is going to be very important. Naturally, it is important for all of signal processing, because remember the Fourier transform or the spectrum of a signal, the decomposition of the signal is very important in signal processing, and in general, of course, naturally when you apply it to images and audio signals and so on, it becomes also very important in machine learning and also naturally in data analytics, right. All of these are interrelated, right. Let us now go to this notion of the norm of a vector. So, what we mean by the norm of a vector? Let us now go to the notion of a norm of a vector, all right. So, the norm of a vector this is denoted by norm u bar, which is nothing but the square root of the inner product of a vector u bar with itself, which is essentially for a real vector. You can clearly see the inner product of u with itself for a real vector u bar u bar u bar u bar, inner product with itself, this is u1 square u2 square plus so on un square, right, which is nothing but u bar transpose u bar, and therefore, this norm of u bar, or what you also call as L2 norm of u bar, which is what we are going to use by default, is going to be square root of u1 square plus u2 square plus un square, right. And this is also what we call as the length of a vector in a 3-dimensional space, or in general length. This is essentially the length of a vector. And for complex vectors, so this is for real vectors where u1, u2, un are real. For complex vectors, this will be simply the magnitude, that is mod of u1 square right. So, this is simply the magnitude of u1 square plus u2 square plus so on up to un square, and so this is for a complex vector. This definition is for a complex vector, and it is very easy to see norm u bar square, that is norm of u bar is greater than or equal to 0, and this is equal to 0, norm of u bar equal to 0 if and only if this is implies and is implied by u bar equal to 0. That is, the norm or length of a vector equal to 0 only if u bar equal to 0, which means every ui, which means essentially every ui equal to 0, alright. So, this is essentially the norm of a vector, which is defined as square root of u1 square plus u2 square plus un square for a real vector, and square root of magnitude u1 square plus magnitude u2 square plus magnitude un square for a complex vector, and this is always greater than or equal to 0 except for a vector u bar which is identically equal to 0, that is u1, u2, un, all the elements are 0. Alright, so let us stop this module here and let us continue in the next module with further discussion on these various concepts of applied linear algebra. Thank you very much.